Okay, so one of the things that we discussed in class was the work-energy theorem. And I'm not going to write right now how to come up with it, but basically it says the work net is equal to KEF minus KEI. Okay, where the kinetic energy is equal to 1/2 the mass times the velocity squared. Now, of course, if we have the final, we would put the final in here. If we have the initial, we would put the initial in here for the velocity. And so let's say we have a car. My drawings are the greatest. No need to leave comments. And let's say that there's a force on the car of 200 newtons. Okay, and we're going to say that the car starts at 0. So the initial velocity is 0. And we're going to say that it's displaced 100 meters. Okay. All right, so the 200 Newton force is going to be constant. We have a displacement of 100 meters, and we have an initial velocity of 0. I want to know over here, what is the final kinetic energy? And I want to know what the final velocity is. And I like this problem for multiple reasons, but I really like it because it allows us to see how work right here is directly related to the energy. Okay? Now, in our equation, the initial velocity is 0 due to, the kinetic energy is 0 due to our initial velocity being 0. And so I'm going to write my equation as W net, or the net work, you can just write W if you would like, is equal to KEF. Now, the one thing that we do know from in class is that work is also equal to the force times the displacement. Now, you'll notice in my equation here that I don't have any angles. And the reason is because our force of 200 newtons is directly in line with the motion, which is the x direction. Right. So you see here that we have our force of 200 newtons and we have our displacement. So I'm going to multiply those. It's equal to 200 newtons times 100 meters. Now, I was a little bit maybe confusing there, but we're going to say that's a significant digit. So 100 times 200, 4 zeros, and it's joules. Okay. Now, based off of this right here, and the fact that we know that work and energy are very much related, and basically they're the same thing, so I put 20,000 joules of energy into the object to speed it up to here. So I also put 20,000 joules of work into the object, which is a car, to speed it up to this point. So therefore, I would know that the kinetic energy would be equal to 20,000 joules. Okay, so that solves my first question. And then lastly, we want to find the kinetic energy. So kinetic energy is equal to 1/2 mv squared. I'm going to solve for my final velocity, and you can check and run through the algebra, but that's basically the algebra right there. All right. And so when I plug my numbers in, 2 times 20,000, then divided by the mass. Okay. I guess I ran into a little bit of problem where I did not write down what the mass was, so let's make one up right now. Let's say it's a really tiny car, and it's 10 kilograms. Okay. So we would assume that that would be given to you at the beginning. So 2 times 20,000 is 40,000. Divided by 10 will give us square root of, what is that? 2,000. The units I'm sort of just
doing there without really explaining them. You can work through those units and you would find that that's true. So I have square root of 2,000 would be 45. If I look at the significant figures and I go with 2 for my mass, because it's 10 kilograms, my answer is 45 meters per second. So there we go. So that's basically how we use the work energy theorem to calculate our final velocities. I'm going to add a little bit more to this, because some students' first inkling is not to do it this way. Okay? When they see a mass and a force given, the first thing they think of is kinematic equations. So we'll see how messy this gets by me erasing. Okay, I think we can leave. Yeah, we could leave all that right there. So here's what students think of. They think, well, I'm looking for the final velocity, and I know my initial velocity is 0, and I have x, and I could solve for a. And so they come up with what we call the second kinematic equation. I know my initial velocity is 0, and let's just solve for final velocity right here. Or let's solve for the ax, because this is how I did it in class. And so vf squared divided by 2 is equal to ax. Okay? And I just want to make a little note of this right here. And that looks kind of goofy. Like we've never done anything in class that ended up looking like that. But that's fine. I'm going to prove a point. So there that is right there. There that is. Okay, now I'm going to look at my work right here. Now I know that work is equal to F times X, and F is equal to MA. Okay. I also know, so this is F. Might be hard to see that. And I also know that the work is equal to the kinetic energy. And so 1/2 mvf squared is equal to max. You'll notice that our masses cancel, and look at this right here. 1/2 of vf squared is equal to ax. So you see this? Vf squared divided by 2. This is the same thing, Vf squared divided by 2. Ax, Ax. So actually, it looks a little bit easier in this problem to use our kinematic equations to solve for whatever we're looking for, like the final velocity. But what I'm trying to get you to do is use work and think of the relationship between work and energy, because when it comes to problems on inclines and springs and everything, this is going to be the way to go. This is going to be the much, much easier way. It just happens to work out that it might be a little easier using kinematics because of our flat surface. Okay? So there's a pretty simple problem as far as the work energy theorem. And we solve for the kinetic energy and the final velocity.